OneQuantum Philippines. And first of all, I'd like to thank you for making it to this event. And please allow me to briefly introduce OneQuantum Philippines. So we are a chapter, the Philippine chapter of OneQuantum Global, and our mission is to increase the awareness of Filipinos about quantum technologies. And one way we're doing this is by hosting events like this. So for tonight, we are extremely honored to have a distinguished guest with us from Classiq Technologies. And just like many of the attendees here, I'm also very curious on how Classiq Technologies, how Classiq platform can help me in learning quantum computing. So without further ado, I'm thrilled to introduce Vincent Van Wingerden from Classiq Technologies. So Vincent, the floor is yours.
Hey everybody, thank you so much. So I will, if that's okay, I will share my screen and then do the introductions for everybody from Classiq. Just asking, can you make me a host, because I'm not allowed to share my screen at the moment. So while we figure that out, let me start by introducing ourselves. So it isn't just me. So my name is Vincent. I'm located actually in Amsterdam, and I'm here with two colleagues of mine, namely Hannah and Israel. And maybe you want to introduce yourself also very quickly, say hi, and then we will have probably sorted it out to the sharing issue.
Sure, I'm
So
Hannah.
Hannah, you want to get started?
Yeah.
Perfect.
I'm Hannah. I'm a technical marketer based in America, a little bit outside of Philadelphia, work remotely, and happy to be here.
Perfect.
Hi, I'm Israel. I'm a quantum software engineer working in the R&D department, and I'm based in Israel, and happy to be here. Good luck.
Great. So that's us. That's the entire team. We're here for you today. And during the entire session, always feel free to interrupt me, raise your hand, ask questions in the chat. I know we're with quite a big group, but feel free to make it as interactive as possible. We don't need to make this a one-sided lecture. So always feel free to interact with us. That is something we actually love. So what is our goal for today? Today, I'm going to give a short introduction into Classiq, like what is our platform, why are we doing what we are doing, and after that, basically, we're going to be hands-on. So everybody's going to do these things themselves. So we're not here just to give a presentation. We're actually going to spend most of the time hands-on working with the platform. So also during these things, if you have a question, if you're stuck, feel free to ask questions in the chat because we're here to help you with that. So without further ado, let's get started. And let's get started with what is Classiq? Who are we? So we see ourselves as a leader in the quantum computer software space. We are roughly with 60 people, mostly quantum experts in the field of both algorithms as well as quantum software development. And we have offices in the entire world, basically. And as you can see, we're represented from multiple continents already, from Israel, where our headquarters is, as well as in the US. Japan is an open office, and I am in Amsterdam. So we're quite spread out throughout the world. And our customer base is both enterprise, so large commercial customers, as well as research. So we cater to both of these needs, basically, and that is something we very actively pursue, both research as well as enterprise customers. And one important thing is we're not doing this alone. We don't want to change the world on our own. We want to do that together. So we're working together with a lot of partners in the industry, ranging from hardware vendors like IBM, middle layers like Microsoft, simulators from NVIDIA, but also education partners like the Technical University in Milan, in Munich, who is actually using our software to teach quantum computing and design automation to their students via our platform. And also via applied research institutions like the Fraunhofer Institute in Germany and all other types of institutes. So we are really here to do things together, and that's also why we're here. We don't need to do things on our own. So what is it that we do? We allow you to interactively design quantum algorithms. And this might sound like something that you can already do with other tools. However, during this session, I hope you see the big differentiator between creating algorithms on a higher functional level, what we allow you to do,
recording in progress,
and traditional tools. So that is what we do: enable you to create quantum algorithms at a high level, and then automatically optimize them for you and allow you to execute them either on simulators or on actual quantum hardware. So why do we do that? Why do we even want to do it? If you look at the quantum software development at the moment, we don't have these enormous machines that we have. So the circuits themselves, they cannot be huge, and both in terms of number of qubits as well as in depth. So creating a quantum circuit might still be very doable at the moment when you're running on smaller machines which are freely accessible from IBM, for example. However, the more qubits become available and the higher the fidelity of these qubits are, the larger and more complex the quantum circuits will get or need to get when you want to get these more complex circuits to run and these more complex algorithms to execute something for you. And the more complex it becomes, the more harder it will become with the current tool set, from anything from Cirq to Qiskit to Q#, to build very large-scale quantum circuits which actually run efficiently on different types of hardware. And that is where Classiq comes in. We allow you to have an abstraction layer above the low gate level programming tools that are currently being used. So the first thing we do is we abstract away a lot of that low level gate-based programming. And that allows us to also scale very easily. So when you abstract away the low gate level programming and you program at a very high level, just like we're doing in classical computing, when you're programming Python, you're not thinking about the low level code that happens underneath. You want to program at a high level and describe the functionality that you want instead of implement that functionality in a very low level. And that is what we do. And with that high abstraction, we allow for a lot of scalability. So the idea is you describe your problem once in a high abstraction level, and then with the use of what we call our synthesis engine, you feed in that high level functional description of your program, and our synthesis engine will then generate a gate-based quantum circuit for you. And the nice thing is, once your computer grows, or you have a different type of qubit, you have a different type of connectivity map, you have more qubits available, you do not need to reprogram. The synthesis engine will recreate that gate-based program for you. So when larger computers become available, you don't have to do anything yourself. You don't have to rewrite any code. So that makes it very scalable. And that makes it also very usable because you're not programming on this very low level. You're able to easily describe functions on a higher level, which makes it easier to collaborate on your code as well, because you're not playing around at this very low level. So this is what Classiq set out to do. Make programming for quantum computers easier by abstraction. And with that abstraction, we allow for higher scalability and easier usability. And one important feature, which I forgot from usability, is also we want to allow people to become developers for quantum computers without the need to have a PhD in quantum mechanics. So we want everybody to be enabled to program quantum computers. And we believe that to enable that, you will need a higher abstraction layer, because not everybody will be able to program at this low gate level. So I see there's a lot of questions in chat, and I'm just gonna quickly look at Hannah. Is there a question which we need to answer for the group or not? I see you're still on mute, just FYI.
Yeah, within the meeting chat, all I see are welcomes.
Okay, perfect. I just saw the pop-up, so that's why I was asking. Good. And again, if there's any questions, either feel free to interrupt me or put them in the chat, and I will probably give me a quick heads up that I need to answer it. So how does it work? How do we do that? How do we change? How do we go from a high abstraction level to a low gate-based program? Inside of the Classiq platform, we have various tools. The first tool is one of the tools which we'll be working with in a few minutes, actually, is our modeling tool. Our modeling tool is an interactive online development environment, which allows you to actually very easily create quantum algorithms from a high descriptive language. And when you have properly described the functionality that you want from your quantum program, our synthesis engine will turn that high-level description into an actual quantum circuit. When you have a quantum circuit, you are able to actually use our visualization tool to dive deeper into what is actually happening inside of that quantum circuit. What happens if I would change a specific target? Is there a difference if I target IBM versus Azure? Is there a difference when I optimize for depth or whether I optimize for width? What happens to my output program when I change all these parameters? And that is what you can very easily do inside of our visualizer. And once you have that circuit that you're happy with, the right amount of qubits are being used, it is as shallow as you want it, it uses the right approaches to these subroutines, for example, then the next step, of course, is to execute it. And because we're able to export our circuits into any gate-based programming, whether it is QASM, whether it's Turk, whether it's Q#, QIR, you name it, we can basically address any gate-based quantum computer that's available. And because we allow you to export your code very easily, even if you don't want to execute it via the Classiq platform, we will allow you to export your code in QASM, Q# or whatever is needed, and you can manually execute it wherever you would like. So even if you have a secret quantum computer in your basement, you can use Classiq to actually synthesize the code and execute it on your own quantum device. So we give a lot of flexibility. We don't want to hook you into the platform. It's very easy to take out the generated code that you have. So if we break it down a little bit more, even to all the different parts in our stack, and let's start from the top, we have these two tools to create, to code basically for our platform. The first one is the online environment, which I just showed, and that's something that we will use today, which is called our IDE, which is a low-code browser-based programming environment. But also for the more advanced users, we have a Python SDK, which is for the more advanced programmers, probably easier to use. And from both these environments, you're able to readily use complete applications which we built for finance, for example, or you can build your own algorithms from scratch, even creating the lowest subroutines if you would like, or anything in between. Use our blocks that we have already created, and from those blocks create a larger algorithm that you want. Once you have that modeling done, either completely by yourself or using part of our built-in programs, you can synthesize those programs for a specific target. So that can be a real machine, so that can be an IBM machine. But you're also able to set your own machine, describe your own machine. So, for example, describe how many qubits it has, the type of connectivity that has, or the type of native gates that that machine can execute. And this could very much help you in algorithmic research. How would a specific algorithm fit on a piece of hardware which might not even exist or that you are thinking about? And then when you have created that circuit for either a real machine or from your own machine, you can use our analysis tool to see how that would actually execute on that machine. So even you're able to compare various hardwares, or you're able to see how's each qubit being used? Are some qubits overused, various other qubits? How's the connectivity between all the qubits? You name it. So a very comprehensive analysis suite is available. And then, as I said before, you're able to execute anywhere you would like, either in the cloud or your own universal gate-based quantum computer. Any questions so far? Cool. So how does it look? And this is something that we will see later today. So there's, as I said, there's two ways of actually programming for Classiq. One, there's this high level, what we call QMods, which look like JSON files, which describe which describes the functionality of your program, and then from that create a gate-based circuit. So on the left, So on the left you see some logical flow, and that logical flow is actually the functionality that your algorithm has. So most algorithms have various sub-steps, starting with a state preparation and then maybe doing a phase estimation or whatever is happening. Inside of our logical flow, you're able to describe exactly what happens there. And in this case, it describes a specific arithmetic oracle, which you can use inside of Grover, or you can use in any other type any other algorithm that you would like to do. So a little bit of how does Classiq compares to the other tools. So one of the things that we pride ourselves on is the hardware aware functionality and adding auxiliary qubits to algorithms where possible. And with that, you're able to get way more efficient algorithm or circuits if we automatically add things like auxiliary qubits, and we see a great improvement in the amounts of qubits that are needed or the depth that a circuit needs when you want to have a specific functionality. In this case, MCX circuit or a controlled adder.
We have a question, Vincent.
Sure, go ahead.
From Dandel, I'm sorry if I mispronounced that. Any standard or specific system requirements to run the Classiq? What about license?
That's a very good question. And that depends on the purpose that you have. Currently, if you're an academic, then you can use what we call our academic license. If you don't have, which is free, you can sign up at classiq.io. For others, please contact us. But for now, currently, if you're signed up to this workshop, we have given you a license for the duration of I don't know how many days to actually use the tool right now. But if you want to use the tool, just sign up or send a message on the website, and we'll go from there. As far as system requirements, there's no requirements. Today we will be doing just the things online, so a browser is more than enough. And if you want to use the Python SDK, you don't need anything more than a computer running Python, I think 3.8 or higher or something like that. So there's no complex requirements for your system. I hope that answers your question.
And we have another great question.
Sure.
From Jabez, again, apologies. Will Classiq handle the export into different qubit modalities, superconducting, neutral atoms, trapped ions, etc.?
So what we do, and that is also what you see in the analyzer here, is when you want to go from your high-level description language into your specific hardware, which can be, as you said, superconducting or ions or whatever, you also give a description of your hardware to the synthesis engine, if you like. So that can be, for example, the connectivity between the qubits. That can be the native gates that these qubits support. And once you have given that description of those qubits, we will take that into account and create the most optimal circuit for that specific configuration. So that specific qubit connectivity, as well as that those specific native gates that are supported. And once we have done that, once we have created that circuit, you can export it into any format and execute it on any device. So yes, we allow you to basically adopt to any type of modality. So what we see here is a part of the analysis suite, and what you can see, for example, on the right is actually about that. It's the qubit mapping. So here you will see a circuit where qubits are very highly connected, at least on the right side, whereas in other examples you would see only a small connectivity, and that's something you can use to see, well, how will my actual code be run on the device itself. And also in a resource distribution, you can see, are some qubits overused or underutilized, for example. And also we allow you to compare other hardware types. So maybe you've created your circuit for an IBM device, but you want to see what would happen if I would take this circuit and run it on another device, maybe IonQ, maybe Rigetti or something else. We allow you to simply start a quick, what we call hardware comparison, where we compare how your circuit would actually transpile to various hardware, so you can pick the best hardware to run your specific circuit on. As I already said, we can execute on anything, any type of modality, as long as it is gate-based and also simulator. So we've just did a huge execution on a very big NVIDIA simulator. So for us, as long as your computer is able to process gate-based programs, then we're able to execute on that. So as I already said, you're able to create programs completely from scratch, but we also have pre-built blocks as well as pre-built applications. And this is just a small set of pre-built applications, from optimization to option pricing to HHL to machine learning to Shor's algorithm. So there's a lot of different things that are already built in, which you can use, and you don't have to redevelop yourself if you want to use this. So some examples that we have already done. This is an example that we did with Rolls-Royce, who have actually used HHL to do a part of the CFD calculation. And this is, if you're interested, a very nice press release as well. So if you Google Rolls-Royce and Classiq, you see that we created a very large HHL algorithm and executed that on, I think, something like a 39 qubit simulator of NVIDIA. So that was a very, very cool project. As I already said, we're using Classiq inside of the classroom to teach people about quantum computing and design automation. And so for now, I basically want to say, if there's any questions, let me know. And otherwise, we're going to work. So Hannah, any questions, or shall we get started? No questions? Okay.
One just showed up.
Cool. What? Oh, there is?
One just showed up.
Okay, sure, go ahead.
Can we accommodate several modalities in harmony with each other? I also assume that annealing does not relate at all here, right?
Yeah, so we're not supporting annealing at the moment. So D-Wave annealers are not supported. And various modalities, I do not completely understand what you mean. Do you want them inside of one algorithm in one quantum program? In that case, no. If you want to say, well, I have this high level functionality and I want to see how I would synthesize a circuit for one modality, compare it to the other modality, in that case, the answer is yes. So that's very easily done. That's one of the, yeah. And I hope that answers the question. So let's get started. So the first thing we're going to do is I'm going to show you how we're synthesizing circuits with the Classiq platform, and then I will actually ask you to do it yourself. So I will show it once, and then I have some exercises for everybody to do yourself. So later I'll ask everybody, everybody should have access to this link called platform.classiq.io. So if you have subscribed to the workshop, you should have access to it, and you would come into this page. And so the first thing that we're going to do is we're going to synthesize a circuit, and that circuit has one function, and that function is a state preparation. So for a lot of algorithms, we want to encode the data that we have, or something else. We want to start with a state preparation. And in this case, when we go to the synthesis, we already have a built-in state preparation algorithm. And on the left here, you can see our QMod. And our QMod is actually the file that describes the program that we have. So here you can see we have a main file, and inside of the main file, we have a body, and this body describes all the steps we have in our quantum program. And in this case, our quantum program only has a single step, namely a state preparation. And in this case, we want a state preparation to prepare a state on specific probabilities. And these are real and positive probabilities. And so in this case, we're having 5 qubits, and these are the probabilities we want on each specific basis state. So this is 0, 0, 0, 0, 0, 0, 0, 1, etc., all the way down. Next to that, we want to have a specific error metric. Eventually, we need to approximate this state preparation. And the lower the error we will have, you will see the deeper the circuit will get. But we allow you to have a lot of flexibility to actually prepare that error yourself. So if you allow for a higher error, you will actually get a shallower circuit, but then you will have more error in your state preparation. So this is a trade-off that you, as the algorithm designer, need to make yourself. And also, we have a classical function, which is basically, in this case, a sample. So what we do at the end, we want to measure the qubits to actually see what is happening. So now the question is, how do we actually create a quantum program out of that? So here on the right, we have some more probability options. So yeah, Hannah, go ahead.
Brian is asking, you said probabilities. Do you mean amplitudes?
Yes. In this case, Israel, these are the amplitudes, right? The real and positive amplitudes.
If the field name is probabilities, then it's actually the probabilities, so they sum up to 1. But there's also an option to put the amplitudes. Okay.
So in this case, no, it's probabilities, but there's also amplitudes.
We have another question. On On what error correcting algorithms can Classiq support? Can we choose which to use on our circuit?
Yes, you can. And I do not know them all on top of my head. So maybe Israel or Hannah can share the link in the documentation to each one. So, but there are various, but I don't know them all that we support on top of my head. But the answer is yes, we have various algorithms, various error metrics that we actually support. So on the right here, we can actually add some more preferences and constraints for our program. So we can specify the maximum width, which is the maximum number of qubits that we want to use, the maximum depth, the maximum depth that we want. We can add optimization parameters. So for example, optimize for depth. So have the shallowest circuit as possible, or optimize for width, use the least amount of qubits possible. So these are two trade-offs. So we can say, in this case, depth. Then we can also say on our hardware aware side, we want to optimize for a specific backend provider. So for example, IBM Quantum. And in the backend name, we can set, for example, say Gyro. And then the synthesis engine knows the connectivity of this backend and know the native gates that this backend supports. So now what we're going to do is we're going to press synthesize. And what happens now is this function, and you can see also all the parameters that I just have shown up here, are sent to our synthesis engine, and we have created a functional circuit. So on the left, you can see some properties. So you see the depth of the circuit. You see the total amount of qubits that are being used. You can see the native gates that are being used. So X, SX, RZ, and CX. And these should be gates that are specifically supported by this device. If you go in, you can see how is this state preparation created. So we see it started with an equal superposition and using various RY gates, rotations. This is eventually we come to the specific state preparation. What we then can do is say execute. We can execute on any vendor, IBM, Azure, Amazon, whatever you want. And we can have real hardware or simulators. Let's just do the simulator. In this case, the air simulator, which is hosted by Classiq ourselves. And we can have some definitions on the execution. So in this case, the amount of shots, the name of the job, you name it, and we can actually run it. So it will now be in the queue and it will be run. So here we go. And this is the actual state preparation that we got. So let me go back to the slides. Yep.
In the code, there's a parameter defined as num qubits equals 8. How is that affected by the max width constraint?
In this case, because the max width is lower, it won't. It will make sure it doesn't go to 8. So we'll only use 5 qubits. So now it's your turn to do this yourself. So we will give everybody a couple of minutes and we are here in the chat to support everybody. Sorry, that shouldn't be there. Here you go. So we're here to support. Please go to the synthesis page. So that's platform.classiq.io and do initially the same as I did and try to synthesize the circuit first without any specific hardware, and then using a specific hardware, and then execute it using the IBM Air simulator. So if there's questions, if you're stuck, feel free to use the chat, and I'm gonna give everybody a few minutes to actually execute this by yourself. So Anand, can you share maybe your code that you have if you have that error?
Yeah, sure. Sure. Okay, am I allowed to share screen? Okay. No, it's disabled for me. You want me to share a snapshot for that?
So if you can share the code that you have, so the JSON file for in the chat, then we can take a look.
Anand can share.
No, just copy paste the QMods, the JSON file.
model.
Copy your code here. And same goes for Lester. Maybe you can also in a reply copy the code so we can actually look at what's happening for you.
Actually, I didn't change anything in the code. I just saw you, and I think I just tried to. I just selected one parameter, backend service provider, and okay, I haven't selected any backend name. Right. Okay, I'm selecting AS inverter as now it should be. Yeah, now I'm not getting any error. I just selected backend service provider and backend name as air simulator in IBM Quantum. Now it's working fine.
Great. So this is the first check. So if you can use the backend of IBM and once of the Nairobi machine and one time for the IonQ machine, and then look once the circuits are synthesized, look at the difference of the circuits. And maybe if you're done, you can raise your hand in Zoom so I know how many people are done and to see how far along we are. But don't rush yet. We'll still have some time.
Can you go back to the previous slide? I'm just doing that part.
Sure. Anand, are you okay? I haven't seen the code yet, so I hope that your error is fixed. Done. Okay. Dylan,
Yeah,
maybe you can.
Okay, now I'm getting a. No, I'm getting a different error. Axios error, network error. I don't know. Doing something like this. Axios error, network error.
X.
So David, maybe you can use not the simulator of IonQ, and the reason is it has a very big gate set, which is not available to everybody. So instead of using IonQ simulator, use the Azure Quantum, and then as a backend name, use just IonQ. So also for Abdel Lali, maybe you can use instead of using the simulator, use the actual quantum chip. So if you in the backend service provider have Azure Quantum in your code, and then the backend name. So I will go to the next slide. Here you can see the specification. And later, when everybody is done, I will give you a reason why that is important. And Ricardo, yes, actually, that is the output you need to see as a circuit. So there's no IonQ in the choice. That's correct. You can actually that's something that we're fixing. So in the code yourself. So once you click IonQ.QPU, you can actually in the code yourself change it to just IonQ. So that's a bit of a bug currently in the selection, but you can just overwrite it in the code yourself. Cool. I see a lot of people are done. I'm giving a little bit more time to make sure everybody had enough time to try it, and there will be more than enough things to do. Do you mean preferences tab and synthesis, or in the execution part? The synthesis part. So in the execution, you can just use the IBM Air simulator.
Lester, you can also post the code in the Slack channel.
Yeah, how do you override to the IOQ? Where put it?
So in the left side, you can actually say, if you in a drop down select Azure Quantum and then IonQ QPU, in the left side, if you drop down, if you scroll all the way down, you will see preferences, backend service provider, and then backend name. And you can simply just delete the QPU part. A lot of people are done. That's good. We're getting somewhere. I'm going to give 3 more minutes, and then I'm going to show the results myself as well to make sure everybody had time to do it.
I've created the circuits, but how do you compare them?
There a new tab should. I think you should just look at the results yourself. There's no specific automatic comparison. You just look at the outputs yourself.
Okay, makes sense. Yeah.
Okay, see Neil's done as well. 2 more minutes. Okay. Final minutes, and then I'll show the results. So the credentials are used only, are not needed if you select the IBM Quantum and then specifically the air simulator. You do not need to put in any credentials. So, okay, I'm going to share my screen again, my other screen, and I'm going to show you what the idea was of the exercise. So here we have our state preparation, and we in this case we won't select any backend preferences. So what is happening then is our synthesis engine will assume that the backend where we're going to run on has an all-in-all connectivity, as well as it has a very large set of native gates that are supported. Unfortunately, in the real world, if you want to execute on a quantum device, that isn't the case. So let's get started with just showing how to create the circuit without any backend. So if we now press synthesize, then we will get this circuit, which is quite shallow, 252 depth. It uses 5 qubits, and these gates are being used as U and CX gates. The unfortunate thing is these gates are not gates that are implemented in a real quantum computer. So what would happen if we would execute this specific circuit? This circuit will need to get transpiled. So a transpiler will actually change how this circuit looks to the native gates that are supported on the real quantum machine. In that process, there can a lot of inefficiencies can creep in. So in Classiq, we don't want to transpile circuits. We want to, when we create the circuit, so in the synthesis phase, we want to already give the synthesis engine information about the quantum computer that you're going to run on. With that in mind, actually the synthesis engine can create a lot more efficient circuits than a transpiler. So in our case, if we would say, for example, Azure Quantum, and we would take the IonQ machine, and unfortunately at the moment, we need to change this a bit, and we say synthesize, what is actually happening is that the synthesis engine now knows, oh, I'm going to synthesize for different machines. So it knows that it's going to pick the IonQ device. And that IonQ device does not have that U gate. So as you can see, the depth has increased a bit, but also it's these are the actual gates that are supported on the IonQ device. So this is what we call hardware-aware synthesis. So from the start, the synthesis engine knows what type of machine you have to create the most efficient circuit as possible. So if we would then do the same, but for example, use an IBM machine, so IBM Cairo, and then synthesize again, you would see that again, the properties of the circuit will completely change because the IBM machine has different native gates and a different connectivity. So this circuit has a lot more depth. One reason could be that it isn't all null connected, just like the IonQ machine. So if we compare these three circuits, they all have exactly the same functionality, but because they are targeting different hardware, it has a different, these circuits are different, differently implementing the same functionality. So no hardware selected, it's very shallow, and this is the IonQ device. It has other native gates. These are supported on an IonQ device, and the same functionality for an IBM device, and again, different implementation. So I hope that clarifies a little bit of what is happening here. And so if you would execute these, all the circuits should give exactly the same results. The only difference is that if you would execute them on a real quantum machine, they are very optimized for that specific machine. And that is something that we really want. We want the most optimal machine, optimal circuit for each specific machine, especially because of the high errors that we still have on these devices. So I hope that clarifies a lot of things. So when we select Azure Quantum, there's no need to backend name. So in the synthesis, what I've done here in Azure Quantum, this is a little bug. The only thing is we need to remove this part. So in the code, you still see there is a backend name. This will change hopefully as soon as possible. Then you can just use the drop down. So this is only now a small bug in the platform, and we will fix that as soon as possible. So just checking, does everybody get this sense of hardware-aware synthesis passing your quantum device into the synthesis engine so we can actually create? Okay, perfect. I see yes, yes. I'm just going to assume that that is a good average for the rest of the group. Next, we're going to do something more complex. So I'm just curious here, maybe we can do some thumbs up or something, or some comments in the chat. Is everybody aware here of Grover search, of Grover's algorithm? Yes, see some thumbs up already. Yep, okay, amazing. That's good, that's good news. Oh, I see one no. Then let's give a very brief, I'm not going to explain how it works. I'm just going to explain what it will achieve. So the Grover search algorithm allows you to search for a specific value, to do some unstructured search, basically. And that unstructured search can be used for databases, although I wonder whether that's the right use case, but you could also use that unstructured search to, for example, solve equations. So if you have a large equations with a lot of variables, you can search what are values of these variables that could actually satisfy a specific mathematical function, for example. So that is also one thing that can be done using the Classiq platform. So on the left, let's take a look here on Grover search. And in this case, we can ignore this part a bit more. And on the right side, what you see is a specific mathematical expression. So A plus B plus this whole part eventually equals 4. How does this compare to Grover? We can ask Grover to find values of variable A, B, and C, arrow C, which satisfies that eventually this part of the equation equals 4. So that is an unstructured search, and we would like to use Grover to find these values for the variables. If you will use a traditional language, it will be difficult to create this entire oracle to solve it and the entire code to solve it. Luckily, using Classiq, the only thing you need to do is give this expression. So this is the expression that we want to solve. And we need to give some definition on the variable. So in this case, variable A has a size of 2. That means that it uses a quantum register size of 2. So this specific variable can assume 4 integer values, 0, 1, 2, and 3, because it just uses 2 qubits. And this can use more, can use 8 values. So this gives some description on the variables that are being used here. In the SDK, you can even add more properties of these variables. For example, do you want to add decimal numbers? Do you want them to be signed, or do you want them to be unsigned? Next, we can also give the same optimization parameters as we did before. For example, we want to optimize depth. So now what we can do is say synthesize. And what this will do is this will create a Grover search algorithm which will find these values. So this is the algorithm that has been created. And let's zoom in. So a Grover search algorithm normally starts with this superposition, then it has a Grover operator. So this is the oracle. Then we have a diffuser. So let's look at the oracle. This is the arithmetic oracle which is being created. And this oracle actually implements the mathematical expression that we have just shown. So imagine if you go down here, imagine having to manually program all these steps. What you also see is it uses for the Grover diffuser, there is a large MCX gate here. And what you can see, it actually is using multiple auxiliary qubits to make this operation as efficient as possible. So it automatically adds auxiliary qubits to have a more efficient circuit. So we're reducing the depth by adding more qubits, and therefore allowing to have less depth. But like we've seen before, it still uses this U-gate, which isn't something that a real quantum computer can do. So in the synthesis, if we would, for example, say we want to use a real quantum computer, for example, Washington, which has a lot of qubits, and we can synthesize again, you will see that also how that Grover diffuser is implemented is completely different. The reason it is different is because the synthesis engine actually understands how it looks, how the QPU, how the real quantum hardware looks. So you see the depth has exploded. There's only the native gates are supported here, but as you can see, when I compare it, 1 second, expand it, the arithmetic oracle, it looks very much different than the oracle which is being used for the other machine. So we take into account how what can the quantum computer do and optimize for that specifically. And with that, we get these very efficient quantum circuits. So now what we can also do is say execute. Let's execute the one which has, let's execute this one. It was a lot shallower. And we're going to execute it on the air simulator. And we're going to press run. And it's now executing. And what it should return with is the values of each variable. And I'm not sure why I'm not seeing that right now. Let me check a bit. What I expected to see was actually the results of each variables. So what were the values of each variable which eventually would satisfy this specific expression? So while I'm figuring that out, I'm going to share my slides again. Here we go. And I'm going to give everybody the next exercise. So this is the exercise. And I'm going to explain it a bit more, in a bit more detail. If we have this shape, which is called trapezoid, then what we want to have is we want to have this specific shape, and we want a shape with a surface area of 10. So this is what we want, a surface area of 10. And Bill, you know the platform, the Classiq platform better than me. I'll show it later. You are completely correct. Thank you for that. So what we want actually is a trapezoid has a surface of 10. So the question is, what should the dimensions be of B and A and the height? So 3 variables, A, B, and the height, to get a trapezoid which has a total surface area of 10. So that's the question. And the question is, can we actually solve this question with Grover search? So can we use Grover to find a trapezoid with a surface area of 10? So this is a function to calculate the surface area. So you do A plus B, you divide it by 2, and you do it times H. So the question for you is, use everything I just shown you to actually do this. So create a Grover's algorithm, generate an expression that will satisfy this function to 10, have a maximum width of 24 qubits, optimize for depth, and use the air simulator for execution. And this is not needed anymore. So the question is, what are your results? And I will also quickly share. So one thing which I didn't know is here you are actually able, so the results of the variables are right here. So Bill just pointed that out to me. Thank you very much. So these are the results specifically for each variable. So I would say I'm going to bring back the PowerPoint presentation, and I would say good luck. I assume there will be a lot of questions, so feel free to ask, and let's see what the results are. So you can change the size of each variable. You're allowed, that's okay. You can also change the size of 10. Just make sure that the width of the circuit doesn't exceed 24. So Ray, you're already done. That is super quick. Maybe you can share the values of your variables to validate that we are actually that you have satisfied that you have created a trapezoid with a surface area of 10. So David, maybe you can share the execution results so we know that you have actually created a trapezoid with a which have this specific surface area. So both David and Leonard, maybe you can create a response in your messages to create the execution, to share the execution results.
How do I share it? Like just share the JSON file?
No, I mean just in the documents. Just say just type it here. Like, what is your value of A? What is your value of B? And what is your value of C?
I guess I need a token, right? I need to get my token first.
No, if you use the IBM Air simulator, so in the execution page, you use IBM Quantum and then select the Air simulator, you actually do not need to have a token. You can execute it without any token.
I pick a quantum, that's why. Yeah, that's right.
Also, Shahad, can you share the results of your execution? And Anand as well, maybe you can share the results of the execution.
Hello.
Hi.
Sorry for the disruption. Can I share the JSON file or just
Sure,
the
you can
results?
put it inside of the I see one file's already shared.
Yeah.
So yeah.
I HTML file.
Or maybe you can share a screenshot. That would also be fine.
Thank you.
Hey, Vincent, I have a question.
Yes.
Can we go back to the previous example, which is the default example? I just wanted to ask how you're able to get the answer of the growth.
Yeah. So this is the answer now for the trapezoid, and this is the one for the default. So if you go here, you have the execution results. You can actually go to the results of A, the results of variable B, and the results of C. So if you have variable A, this would mean this would be the integer value of 3. This is also the integer value of 3. And C, I would quickly have to check what that how much, what this value is. So I will quickly check how to get the integer values out of this. If I share my presentation, this is what we would get, is the variable and the value of each variable. So this is what we should get for, this is one possibility of the initial result.
Okay. So there are so many combinations of answers.
Exactly. It doesn't mean that there is a single answer which is correct.
Okay.
And that's the idea of Grover. So it could get various answer. It could get various results. I mean, also with the trapezoid example I just shared, there is various answers which are actually the right answer, which solve that question.
Do you have like an example which just gives one result?
Yeah, so that's you can choose any, you can create your own mathematical expression which only has one result. For example, you can say, if it's a plus value, you can say, for example, a plus b equals 0. Then it should only get a single result, which is a and b are 0.
Okay. Okay. Thank you for that.
You're welcome. Neil, I will share the docs link to actually have that for you.
Hey, listen, I shared again. Can you just see if it's okay? I've shared the image this time. After execute. Last time I didn't execute actually.
I can't really hear you. Maybe that is my sound, but I can really hear you. Can you put it in the chat? The optimized depth is read actually in the is read in the synthesis page. Please take image. Okay, sure. I will check it. Well, that is the right. So Anand, that is the right answer for the state preparation for the Grover search, but not for the trapezoid. So the result for the trapezoid, I will share my screen. Guess we just have 14 minutes left. I will show you how it's done. So this is the right result for the trapezoid. So how did I get to that? This is the expression I used. So a plus b divided by 2 equals the height, and then that equals to 10. And then I can optimize it for depth if I would like. I can synthesize that. Yeah,
I forget the maximum width. 24.
You're completely right. You are completely right. Maximum width of 24. Otherwise, the synthesis cannot do it. So, yeah, you are completely right. Sorry. You are better at Classiq than I am.
Hi me now.
Okay, so I have a 24, and so this is the Grover operator that we get. This is the entire oracle. Here we go. This is what we should have. And then when we go to the execution, and Lester, this will directly also answer your question, you can pick here your vendor, IBM, and we just use a simulator. We press the air simulator and we press run. And it's a bit of a bigger circuit, so it could take some time to run. Yep. There we go. So these are the results. So the results of variable A, B, C, or the complete circuit. So if we would then translate that to integers, you would get a variable A of 3, B of 1, and C of 5. So this will give you an actual trapezoid of size 10. So 3 plus 1 is 4, divided by 2 is 2, times the height, 5 is 10. So this is a valid result for that specific question that we got. And I think there have been already quite a lot of questions. So maybe before we move on, we can get some questions in, and probably then we can use some of that time. And after which there is also some time for the organization to close it off. So, but firstly, let's get started with some questions. There must be some questions.
Yeah. Is it okay if you share your JSON?
Of course. Maybe I should. This one is pretty big, but I'll share it.
Oh, okay. Or probably the only thing that's important there is the arithmetic operation, right?
Exactly. Let me share that in the chat. So I have put that in the chat right now. So if you have that and press the generate model, then the JSON would automatically update, and make sure you set the maximum maximum width in the optimization parameter. One thing maybe, sorry, before we close out, that I can show you, which is pretty interesting, is if you have your circuit view right here. So this is the specific circuit that I got for my trapezoid problem. If you press this export button, you can export it as anything you like. So GASM, HTML, JPEG, or all formats. So it makes it very easy. I see a question. So yeah, feel free to ask. Come off mute and feel free to ask.
Hi, good evening
Yeah.
or good morning. Yeah, Lester here. Just like to ask, because I first used Qiskit, so I was thinking, do you have a way for Classiq, let's say for example, to customize these gates rather than going through the synthesizer, or just go straight to the gates? Would that be possible?
You can use gates. However, the idea really of Classiq is that you're able to create circuits with millions of depth and thousands of qubits. So then programming on a gate-based level is pretty hard, almost impossible. So you can do it, but it is really easy to it's easier to use the high-level language.
Thank you.
I see a question to quickly show VQE, so I can very quickly show it. So we have a VQE problem right here, where we show H2. And again, actually, the layout is exactly the same. It's just another example. You can generate you have to press generate Hamiltonian, and then synthesize, and then you will get your VQE circuit, and you can also directly execute it. So, Sayat, I see that you have a question. Would you like to come off mute and ask the question? At least I see your hand is raised.
Yeah. Hello.
Hi.
Sorry. I just joined late, so I'm sorry if I have missed something. So,
No
like,
worries.
so how is Classiq like connected with IBM real quantum computers? Like how it use real quantum computers to run this or program?
So the programs that we have seen so far are too complex to run on real hardware. So there will be more error than useful results. However, what you can do is if you have the credits, you can in the execution page go for real hardware. Oh, I see. I don't have anything available to me at the moment, but normally there is real. So here we go. So I can just pick any real hardware from IBM or Azure Quantum, and then say I want to run on this. So maybe I can pick Calcutta and say run, and you even see the connectivity between the qubits. The only thing is you would need your own access API key from IBM Quantum. So you would go to IBM Quantum, grab your access token, your hub, your group, and your project, and if you fill it out, then just click and run.
Okay, I see. Thank you.
Yeah, and if you want to directly run QASM on IBM Quantum, you can simply from the synthesis from the circuit page, you can export your code and run it in IBM Quantum as well. So whatever is preferred for you.
I have a question.
Sure.
Going to the exercise, because I copy pasted the expression that you gave, but I did not get the same probabilities that you got. So I was wondering, maybe did you increase the size of the variables, or did you pick something else aside from the maximum width of 24?
No, the only thing is what you have to make sure is you press this generate model. So then it will.
Okay, so I have to press generate model before synthesis.
Yeah. So what will happen if you do that? It will your this JSON on the left will change. So if we have this expression, the generate model, and then you synthesize it. So specifically when you change this Grover part, then you have to press generate model. If you change the constraint, you don't have to do that.
Oh, okay. Thank you.
Are there any other questions?
I have a question.
Sure, go ahead.
Why the highest value for A is 3? If you look at the values, is 3, is not. I look at probabilities, right? So you look at A, B, and C from results, right? So my H is 5. Yeah, my B is 1, I guess. And my highest value for A is 3, not should be 2, right?
3 and 1 would work. If I share my screen, these are the results I got last time. So your highest value 3 is okay for A or B. So if either B or A is
you don't get 10, right? You should get 10, right? Error should be 10.
Yeah, but if we do 3 plus 1, that equals 4. We divide that by 2, which is
you're right. I mix up. I do the 800 times C.
Oh yeah, no.
Yeah,
so it's
right.
it's A plus B divided by 2 times H. So this is the expression.
It's my 6 o'clock. I'm morning, so I'm not working yet.
Yeah, so no, it should work. So your highest value tree actually is the right one. Yeah,
I have another
if there's any
question.
more questions,
Yeah,
yeah,
I have
sure, go ahead.
So I got the binary of the highest probability because there are only like three of the peaks. So may I know how you read this? Where's A, B, and C? Is A the rightmost?
So here you can also just pick A, B, and C, but there was, and I hope it will come back, a table just like I show you here, which simply shows you the integer values. And I will get back to you how to get this view again to make it a lot easier.
But if you're given a binary, how do you read the A? Where's A? Where's B? And where's C?
I would have to check where that where this is. I will get back to that.
Okay, thank you.
Okay, if there are no further questions, in that case, thank you so much. I really enjoyed being here and working on this with you. And I wish everybody all the best. And thank you so much for having me.
Yeah, thank you so much, Vincent, for giving us this wonderful opportunity to learn about Classiq. So I've heard about Classiq from Brian, and I really didn't look at it. So now I'm really impressed. It's really a good tool to learn quantum computing. So I've been doing my Grover's algorithm by hand, but then this one is really very makes things very easy. So yeah, so thank you very much, and thank you for everyone who is attending, and for your very active participation. So thank you very much, and
Yes.
also for the OneQuantum Philippines who's helping, who organized this. For my teammates, thank you very much. Yeah, so we will be giving. Yeah, so this one is like a certificate of appreciation, Vincent, for. Yeah, so that's. Thank you very much. Yeah, for
Thank you so much.
exceptional contribution, and yeah, thank you. And yeah, so we will be giving out also certificates like this for everyone who is attending. And for those, and also the good thing is Classiq Technologies is going to give certificates to those who will be able to submit answers to the exercises. So I guess, yes, so the exercises will be, I already have them, and we will send them to everyone who has attended. And we will give, so Classiq is going to give 1 week for you to submit your exercise, and then they will give you a certificate. So is that correct, Vincent? Will you be the one giving out the certificates?
Most definite. So I think I have a link that where the exercises are, and there should also be a. So I will put that in the chat right now.
Thank you.
So everybody can click that. There should be a link, and just to check, I think it's sent to Eden, the results. And the only thing left for me to say is please join our Slack channel. Maybe Hannah, you can post the link again in the chat to make sure everybody has it. I mean, that will be great, and that is also where you can share your results, or where you can share any questions that you have.
Yeah, so one last thing. Oh, sorry, actually two last things. So the first thing is I would like to request everyone if they can, you know, momentarily open their cameras so that we can have a photo op. Okay, so my friend here, Edison Macabebe, is going to take a screenshot. Ed, can you give them a cue? Okay, so probably Ed is not. So I'll just be
Yeah,
taking
guys,
screen.
ready when you are.
Okay.
Just keep on smiling. Freeze that smile. All right, that's this for the first page. There are only 2 pages. So this will be the last. Steady. All right, great. Thank you so much.
Okay, thank you, Ed. And one last thing, Ed, can you show the last?
Of course. Yeah.
Slide?
Coming up. Yeah, I think that's last page.
Yeah, so yeah, I actually already mentioned it. So thank you very much, guys, for attending, and thank you very much, Classiq Technologies, for giving us this opportunity. Yeah, really, thank you. Really appreciate it. Thank you.
Thank
You're
you.
very welcome. Bye bye.
Bye
Bye.
bye. Thank you. Yeah, I think we'll just email this as well, probably.
Recording stopped.
you.